everyone, and welcome back. This is part 6 of the series of videos about the security of quantum key distribution. In the last video, we have talked about quantum entropies and quantum information theory. This has concluded the preliminaries that we need to actually talk about quantum key distribution. So after studying quantum systems, composite systems and entanglement, classical information theory, classical entropies, and then finally quantum entropies, we are now ready to actually talk about quantum key distribution protocols. The goal of a quantum key distribution protocol is to establish a secret key between two distant parties that we usually call Alice and Bob. Alice and Bob can then use this key to encrypt and decrypt messages, for example using the one-time pad procedure that we introduced in the first video. But how does a quantum key distribution protocol actually work? Well, we have already seen one example in the first video, which was the BB84 example. We will encounter this example in this video again, but this time studying it in more detail and with more mathematical structure. So in general, we can divide a quantum key distribution protocol into two parts. The first part is the quantum transmission phase. In this phase, all the quantum stuff happens. So here, depending on the protocol, Alice and Bob can send quantum states back and forth. They measure quantum states, or an independent source distributes quantum states. We'll see examples of that. At the end of this phase, all the quantum stuff is done. So at the end of this phase, Alice and Bob both hold a bit string, like a classical bit string. And these bit strings they hold, they are not identical, but they are partially correlated. And they are also partially secure after the quantum phase. Because if they're not secret at all, then you cannot extract any amount of key from them. The second phase is then the classical post-processing phase. In this phase, Alice and Bob take their strings they got from the quantum transmission phase and make an actual key out of them. So they have to correct errors in the strings, and they have to make it like more secret than it was initially, so it can be safely used in the one-time pad encryption scheme, for example. In this video, we only focus on the quantum transmission phase. In this phase, we can further divide it. So there are two possibilities. We can either talk about protocols where quantum states are prepared, sent, and measured, which are called prepare and measure schemes. But there's also a second class of protocols, which is called entanglement-based schemes. In these protocols, Alice doesn't prepare a state and sends it to Bob, but rather Alice and Bob hold entangled pairs of qubits. It doesn't matter how they got these pairs. It is still possible that Alice has prepared those and sent one half to Bob, but we also allow that a third party, which can be friendly or evil, it can even be Eve, who prepared these entangled states and distributed them to Alice and Bob. In this video, we will only focus on the first case, the prepare and measure protocols. We will discuss entanglement-based protocols in the next video. Okay, so the general scheme of a prepare and measure protocol is the following. You have seen the BB84 protocol in the first video, which had exactly this structure. So we have two parties, Alice and Bob, who want to establish a secret key. To achieve this goal, they have a quantum channel that Alice can use to send quantum states to Bob. In general, it would be also possible that Bob sends quantum states to Alice, but we don't consider this possibility here. We only talk about protocols where Alice sends quantum states to Bob. They have a second channel, which is a classical channel. Here, Alice and Bob can both send messages back and forth. The classical channel is authenticated. That means that Alice and Bob can be sure they are talking to each other. This excludes the possibility that, for example, Eve went to Bob's laboratory and simply replaced Bob. Because in that case, it doesn't make any sense to try to establish a secret key between Alice and Bob. So we want to exclude these scenarios. Eve can now listen to the communication between Alice and Bob. And in case of the quantum channel, she can interact with the quantum states that are sent in any way that is allowed by the laws of physics. She can also listen to the classical communication, but in this case, she cannot change the classical communication. She can only listen to it. Okay, so let's get back to the BB84 protocol. It is a great example of a prepare and measure protocol because it was the first protocol that was introduced, and therefore it is very well studied and very well understood. It was introduced in 1984 by Charles Bennett and Gilles Brassard, and it works in the following way. So we begin with Alice's part. Alice chooses two random bit strings, string A and string B. Both consist of 4n bits, and string A is the bit string where the actual key bits are included. The string B determines in which basis the key bit will be encoded. So here, if the bit is 0, this means Alice uses the computational basis, which is also called the Z basis, to encode the bit. And if the bit is 1, then she uses the Hadamard basis, which is also called the X basis. She then uses these two strings to prepare states. So here on the right side, you see quantum states psi AI BI. So the first index AI is the bit from the key bit string A, and the second bit BI is the bit from the basis string B. And since these both bit strings have the length 4n, Alice prepares a tensor product state of 4n qubits. And here I said the bit string B determines the basis. This means that each of the qubits is in one of 4 possible states. So if both bits are 0, then Alice encodes the 0 bit into the computational basis, which is simply the 0 state, which you can see here. If bit A is 1, but bit B is still 0, then we have the 1 state in the computational basis. And similar, we encode the bits 0 and 1 in the Hadamard basis. You have seen these states before. She then sends all these states over to Bob. Bob receives the state, and here in general, these states undergo some sort of quantum channel where everything is included that Eve does and all the losses and the noise in the quantum channel. In our example, we will not include noise that's in the quantum channel or losses in the quantum channel. We will consider an idealized scenario here, but we will talk about what Eve can do with the states. Okay, so this quantum channel I talked about is denoted with a curly E. And so Bob has now received these states, and he announces this fact. So Alice knows Bob has received the states she has sent. He then measures the states, so he gets his own bit strings. Some string A prime, which is the analog of Alice's string A, where the key bits are stored, and a bit string B prime, which notes which basis Bob has chosen for his measurements. So Alice and Bob now both hold 2 bit strings. One bit string, A or A prime, where the actual key bit is stored, and one bit string, B or B prime, where the basis they chose is stored. In the next step, which is called the sifting step, Alice and Bob compare the bases they've used. So Alice announces her bit string B, which stores the choice of basis she has made. And here it is important that Bob previously has announced that he has actually received the qubits, because Alice cannot announce her choice of basis before Bob has received the qubits. Otherwise, Eve would exactly know in which basis she has to measure the qubits. Next, Bob announces the positions where his bit string differs from Alice's bit string, because these are the positions where Bob has chosen a different basis than Alice. And in this case, Bob just gets a completely random result, which doesn't give him any information about the key bit that Alice actually wanted to encode. Therefore, Alice and Bob discard these pairs. So they discard the pairs in their key bit string, which are at the position where the basis bit string differs. After the sifting step, Alice has a string A that is now of length 2n, and Bob has a string A prime also of length 2n, because the probability that Bob chooses the wrong basis is 50%. Therefore, their bit strings B and B prime differ in about 50% of the positions. This is basically the quantum transmission phase. And after this comes the classical post-processing. So now Alice and Bob only use classical messages. And I will shortly talk about the different steps here, but not go into much detail because this is part of another video. So the first step is the parameter estimation step. Here Alice and Bob estimate how much information Eve has gained. Then comes the error correction step, since their strings A and A prime are now correlated, but they are probably not identical. They have to perform some error correction codes to make their strings identical. The last step is the privacy amplification step, because to use the bit strings they have in an actual application as a secret key, they have to make sure that Eve has like almost zero knowledge on the key. So this is basically the protocol, and we now want to investigate how Eve can intercept the protocol and actually gain knowledge about the key. The simplest strategy that she can perform is the so-called intercept and resend strategy. Here, Eve intercepts all the qubits Alice sends, so all the 4n qubits Alice sends to Bob are intercepted by Eve, and because she has no idea which basis Alice has chosen to encode the qubits in, she just has to guess the basis. So she randomly chooses the measurement basis, either the computational basis or the Hadamard basis, and gets some result. In half of the cases, which is 2n cases, she guesses correctly. So the result she gets, her bits, are perfectly correlated with Alice's bits. In the other 2n cases, she has the wrong guess, so the result she gets is completely random. Now, Bob, of course, expects to get some states from Alice, so Eve has to send something. Because she does not have any knowledge about the bases Alice has used, she simply uses her basis choice. So here, it has to be, of course, Eve, who prepares each qubit in the same basis that she has measured it in, and sends it to Bob. Bob then measures the qubits in a randomly chosen basis because, as Eve, Bob doesn't have any knowledge about the actual basis that Alice has chosen. And finally, in the sifting step, Alice and Bob they compare the bases they have used, and they get key bit strings A and A prime, now of length 2n. In n of these cases, so in the bit strings they hold after the sifting step, Alice and Bob are sure they have chosen the same bases for these qubits. So in half of the cases, Alice and Bob chose the same basis, but Eve's basis differs. And if Eve's basis differs, then Bob got a completely random result, since Eve's previous result was also completely random. And completely random means that in half of the cases, he has gotten the right result. So there's no error between Bob and Alice's key bit value. But in the other half of the cases, he got the wrong result. That means in n over 2 cases, they have an error in their key strings, which means the error rate they have is 25%. So if Alice and Bob see such a high error rate in the parameter estimation step, they know that Eve has probably intercepted every qubit Alice has sent, and she has gained quite a lot of knowledge. And therefore, they would probably abort the protocol. We now want to have a closer look at an example. So we want to see how this eavesdropping strategy works, and we will look at the case that Alice sends 10 qubits. For this part of the video, I have to turn off the small video that shows me, because otherwise this table would not fit on one page. So the protocol begins with Alice choosing her key bit string, the bit string A. We have here an example of 10 key bits that she would like to communicate to Bob. The next step is that she chooses the second bit string, the bit string B, that tells her in which basis she has to encode the key bit. Here, as always, C denotes the computational basis and H denotes the Hadamard basis. According to these two bit strings, Alice then prepares the states that she wants to send to Bob. And the choice of these two bits results in the following list of qubit states. So here, when she chooses the key bit 0 in the computational basis, the state that is the result of this is the state psi 00. If she had chosen, for example, the key bit 1 encoded in the Hadamard basis, the corresponding qubit state is psi 11. Alice then sends these quantum states to Bob over the quantum channel. But of course, since we're talking about eavesdropping here, Eve intercepts the states. So she, as we talked about before, she randomly chooses a basis for her measurement. That could be, for example, this list of bases, and then she measures the state. Afterwards, she would prepare a quantum state in the exact same basis that she has used for the measurement to send it over to Bob. So the state she prepares after her measurement is the following. So here, if you look at the first bit, where the state that Alice has sent was psi 00, Eve has chosen the wrong basis to measure in. So Alice's basis was the computational basis, but Eve has chosen to measure the qubit in the Hadamard basis. In this case, she gets a random result. So she randomly gets 0 or 1 as a result, and here we chose 0 as an example. And since she has chosen the Hadamard basis, she has to encode the qubit in the Hadamard basis, which results in the state psi 01, which is not the state that Alice initially wanted to send to Bob. If, on the other hand, Eve has chosen the right basis, which is the case for the second key bit, where Alice has encoded the bit in the computational basis and Eve has measured the bit in the computational basis, then the state she sends to Bob is exactly the state that Alice intended to send to Bob. Because in this case, there's only one possible result that Eve can get, which is 1. Okay, and this holds for all the other states that she intercepted. And in this example, you can see that in 6 cases, which are marked in blue, Eve has chosen the wrong basis. So the state she sends over to Bob is a different one than the one Alice has prepared. And in 4 cases, which are marked green here, Eve has chosen the right basis. So she sends exactly the state that Alice initially prepared over to Bob. Okay, so Bob now receives these states, and he also has to randomly choose a basis to measure them in. This could be, for example, this choice of basis. The result that he gets, the result that he gets from this measurement is this one. So in the first case, he has chosen the same basis that Eve has chosen, and therefore he gets the same bit that Eve got from her measurement, but it is a different basis than the one that Alice has chosen. In the second case, Alice, Eve, and Bob, they all have chosen the same basis, and therefore the key bit that Alice initially prepared is also the one that Bob measures in the end. Now comes the sifting step. So here Alice and Bob, they compare the bases they have chosen, and they discard all the bits who have chosen different bases. Here you can see in 4 cases Bob has chosen a different basis than Alice. Here the Hadamard, where Alice has chosen the computational basis, and so on. And in 6 cases they have chosen the same basis, so they discard 40% of the bits. So the resulting key bits that Bob holds are these 6 bits. And we can now look at different cases here. So first, in gray, you can see those bits where all 3 parties have chosen the same basis. So here, nothing happens basically. The state doesn't change, and therefore the key bit that Alice wanted to send is exactly the one that Bob has measured. Then in blue, you can see the cases where Eve has chosen a different basis than Bob and Alice. And actually her interference with the quantum state, it resulted in an error in the key bit string. So here, the bit that Bob measures in the end is different than the one that Alice initially wanted to send. But of course, even if Eve has chosen the wrong basis, there's a 50% chance that the result that Bob measures in the end is the right one, because the result is random. So it's also possible that he gets the same key bit that Alice initially wanted to send. So in the next step, which is already part of the classical post-processing, the parameter estimation step, Alice and Bob now have to get an estimate for how many errors Eve has introduced. And here, let's say they use half of the sifted key bits to do the parameter estimation, for example, these 3 bits, and they compare the key bits. You can see the first one is wrong, but the other 2 are correct bits. So they conclude that in 1/3 of the cases, Eve has introduced an error. This is equivalent to about 33% of error, which is higher than the estimated error of 25% that we talked about before. So in this case, they would definitely abort the protocol. Of course, because this example only includes 10 qubits, it is not very meaningful in terms of the actual numbers that we get, but I think you get the idea from this example, how the eavesdropping works and how Alice and Bob can detect the eavesdropping. We have now studied in detail how the BB84 protocol works and how eavesdropping of the BB84 protocol works, but of course this is not the only possible prepare and measure protocol. I want to introduce some other protocols which borrow ideas from the BB84 protocol, but they are varied in ways that they account for specific problems that arise in the study of prepare and measure protocols. One of the protocols that I would like to talk about is the 6-state protocol. It is very similar to the BB84 protocol in all the different steps, but it has one difference. The BB84 protocol used the computational basis and the Hadamard basis, which you can also call the Z and the X basis. The 6-state protocol now introduces a third basis, the Y basis. The states that correspond to the Y basis are the ones that we call psi y plus and y minus. And in a vector representation, you can write them as 1 over square root of 2, and the vector 1i, where I is the imaginary unit, or 1 minus I respectively. And the advantage of this protocol is that compared to the BB84 protocol, we now have more possibilities for the states. So in the BB84 protocol, you can see that the X and the Z measurement, they span a plane in the Bloch sphere, like this. But with the third basis, with the Y basis, we now actually span the whole Bloch sphere, which gives us much more possibilities for states. Of course, this means that in the sifting step, Alice and Bob have to discard more bits, because now the probability that Bob has chosen the wrong basis is 2/3 instead of 1/2. But the advantage is that Eve has even less knowledge about which basis she should use to measure the state in. And therefore, she would introduce more errors to the key bit that Alice and Bob can see in the parameter estimation step. And actually, the careful security analysis of both of these protocols has resulted in the fact that given an amount of eavesdropping that Eve performs, the 6-state protocol actually lets you generate a higher secret key rate. So the fraction of secret key bits that you get is higher than in the BB84 protocol. But apart from this choice of bases, that we now have 3 instead of 2 bases, the protocol follows the same steps as the BB84 protocol. And therefore, we will not list all these steps again now. Another protocol is the SARG04 protocol. It is named after the initials of the inventors, and it is tailored to be secure against a very specific attack, which is called the photon number splitting attack. I will explain it shortly. So here you have the scenario of a prepare and measure protocol. Alice prepares some states, sends them over to Bob, and Eve intercepts them. Here I have depicted only the quantum channel, because this is where the attack happens. This attack is an attack that attacks an actual implementation of a protocol. So when we use, for example, the polarization of photons to encode our qubits, then what we actually need is a perfect single photon source. These kind of ideal single photon sources do not exist in reality. So what experimentalists do is they use, for example, weak laser pulses to encode the qubits. And these weak laser pulses, so in general, it is the case that like in 90% of the times, there is actually no photon. But in the other 10% of the times, there's one single photon, which is the case we would like to have. But sometimes there are more photons, so 2 photons or 3 photons. And the more photons are together in one pulse, the lower the probability is that this happens. Okay, so in this case, Eve can perform a specific attack. So if the laser pulse contains more than one photon, then all these photons contain the information, so the key bit that Alice wants to send. So if there are, for example, 3 photons in one pulse, then Eve can simply take one of these photons and store it in the quantum memory. In that case, Bob still receives some of the photons, so he announces he has received photons, and at some point Alice will announce her basis. And they don't recognize that Eve has stolen away one of the photons. But this is very dangerous, because Eve has this photon, she stores it in her quantum memory, and then Alice will announce the basis she has used for the encoding. Then Eve can simply listen to that information, use the right basis to measure her photon, and she gets a perfectly correlated bit value. So in all the cases where there are more than one photon, Eve can gain perfect knowledge about the key. And it is very difficult for Alice and Bob to detect this attack, because Eve doesn't introduce any errors in the photons that Bob receives. And for the BB84 protocol, this attack is very severe. So people have looked for help. They have thought about how to change the protocol such that they are secure against this photon number splitting attack. And one possibility is exactly this protocol, the SARG04 protocol. In a later video, we will talk about the photon number splitting attack in more detail. But for now, we will use it as an example of a protocol where the sifting step differs from the previous protocols. Let's have a look at what the sifting step looks like in this protocol, because the protocol is actually very similar to the BB84 protocol. It uses the same states for encoding and decoding, so I've depicted them here again, so you know what we're talking about. We have the X and the Z measurement and these 4 possible states. But the sifting step works differently. Okay, it is most easy to see how it works considering an example. So we'll go through one. Suppose the state that Alice has sent is psi00. In this case, you shouldn't think of the first bit as the key bit and the second bit of the basis bit, because the key bit is not necessarily the first bit here. But we'll see how it works. So this is the state she prepared and she sent over to Bob. After Bob has measured the state he had received, Alice announces a pair of states. The pair she chooses is psi00 and psi01. So it is important that one of the states of the pair is the state she has actually sent, and the other one is a state from the other basis. So here the state she has sent is in the Z basis, so the second half of the pair has to be a state of the X basis. But it doesn't matter which one. I could also have chosen the state psi11 here. Okay, and then she notes 0 as the secret key bit. Why 0? Because the 0 means that the state that she has actually prepared and sent was in the computational basis. So you see the secret key bit here is actually determined by the basis she has used for the encoding. So Bob now has to look at his measurement result and decide whether the bit is valid or invalid. It is valid if Bob can actually distinguish between the 2 candidate states. So if he, from his measurement result, if he can then conclude which of the states was the one Alice has sent, because then he knows the secret key bit. Okay, let's go through the different possibilities. Suppose he has chosen the basis, the computational basis or the Z basis to measure the qubit. In that case, he gets the state psi00, because it is the only possibility if Alice has also prepared the state in this basis. But he would have also gotten this result if the actual state was psi01. Because if Alice had sent the state psi01 and Bob has measured in the computational basis, he would have gotten with equal probability the state psi00 here, or the state psi10. So the state, his measurement result psi00, is consistent with both of the candidate states, and so he cannot actually conclude which was the state Alice has sent. So he announces that the bit is invalid. The second scenario is that Bob chooses the Hadamard basis to measure the bit. In this case, he gets a random result. So he either gets the state psi01 or the state psi11. If the outcome is psi01, the bit is invalid, because as in the previous case, this is consistent with both of the candidate states. Because if the state that Alice has sent was psi00, as we described it here, then Bob simply gets a random result. And if the state that Alice had sent was actually psi01, then psi01 would also have been the outcome of Bob's measurement in the Hadamard basis. Okay, so in this case, again, the bit is invalid. But if Bob's outcome is psi11, then the bit is valid, because this can only happen if the state that Alice has sent is psi00. In the other case, if Alice had sent the state psi01, so she has chosen the Hadamard basis to encode the bit, and Bob measures in the Hadamard basis, the only possible result is psi01. So from his outcome psi11, he knows Alice must have sent the state psi00, and therefore the secret key bit is 0, according to the computational basis that Alice has chosen to encode her bit. Of course, this sifting procedure is much more difficult than the one we have talked about in the BB84 protocol. And also, Bob and Alice have to discard more qubits, like more bits than in the previous case, because here, in more cases, the bit will be invalid. But the advantage is that Alice never actually has to announce the basis that she has used for the encoding. So, coming back to the photon number splitting attack, if Eve has stored her photon, she never gets the information in which basis she has to measure the bit. So it was shown that for the photon number splitting attack, this protocol is actually secure, but for other attacks, other protocols are superior than this one. So this is really tailored to the one specific attack. So we come to the end of the video. In this video, we have seen examples of prepare and measure protocols, and using these examples, we have studied the different steps of a prepare and measure protocol and also have investigated how eavesdropping works. And in the next video, we will talk about entanglement-based protocols. So that are protocols that exploit the properties of entangled states between Alice and Bob to establish a secret key. And we also want to talk about how these two kind of protocols are actually equivalent descriptions of protocols. So thank you for watching, and I hope to see you in the next video.